Good morning, dear students. Welcome back to physics class. For today's class, I am going to discuss mainly on four topics. They are A. Degrees of freedom and law of equipartition of energy. B. Specific heat capacity for monoatomic gases, diatomic gases and polyatomic gases. C. Specific heat capacity for solids, and D. Mean free path. The first topic is degrees of freedom. What do you mean by degrees of freedom? The degrees of freedom of a dynamical system are defined as the total number of coordinates or independent quantities required to describe completely the position and configuration of the system. Configuration means arrangement of constituent atoms of the system in the space. Degree of freedom shows independent ways in which the particles of the system can absorb energy. Consider a system with just one particle present. Suppose if the particle moves along a straight line, we have to use one coordinate, which may be x coordinate, to specify its position. So it has one translational degree of freedom. Suppose if the same particle moves along a plane, we may choose two coordinates which are x and y to specify its position. Then it will have two translational degrees of freedom. And if the particle moves in space, we have to use three coordinates which are x, y and z to specify its position. Then it should have three translational degrees of freedom. For simplicity, consider a room, and if you tie a thick rope from one wall to another, take a ball which is moving straight on the rope. The ball has only one degree of freedom. It is the translational degree of freedom, as it is moving in one particular direction. Consider if the ball is on the floor, which is two-dimensional, then the ball can move along two directions. Thus, it has two translational degree of freedoms. And consider if you throw the ball in space, which is three-dimensional, then the ball can move in three dimensions. Therefore, degree of freedom tells us in how many ways a body can move or rotate or vibrate. Let us see what are the categories of degrees of freedom. There are three types of degrees of freedom. First one is translational degree of freedom. Second one is rotational degree of freedom. And third one is vibrational degree of freedom. First one is translational degree of freedom. It means motion of a body as whole from one point to another. For example, consider the oxygen molecule. It has two oxygen atoms which are bonded together. It is the diatomic molecules since it has two atoms. These two oxygen atoms along with this bond are considered as a whole body. When the body as whole is moving from one point to another, it is in translational motion. Consider a molecule which is free to move in space, and so it will need three coordinates x, y and z to specify its location. Then it will have 3 translational degrees of freedom. In addition to translational degree of freedom, oxygen can also acquire 2 other degree of freedom, which are rotational and vibrational degree of freedom. It should be noticed that molecules of monoatomic gas will have only translational degrees of freedom because they are having only one atom. For example, helium atom consisted of only one helium atom will have only translational degrees of freedom. Each translational degree of freedom contributes a term that contains square of some variable of this motion. This variable is nothing, it is the velocity. This velocity may be either Vx or Vy or Vz. Since each translational degree of freedom represents each axis, the term, which may be 1 by 2 m Vs square or 1 by 2 m Vy square or 1 by 2 m Vz square, will contribute to energy. This is the average kinetic energy which is involved with the motion of a single molecule from one point to another. That means it is in the translatory mode of motion. In thermal equilibrium, the average of each such term will be equal to 1 by 2 kBT, where kB be the Boltzmann constant and T be the absolute temperature. The given figure shows 3 possible translational motion of a monoatomic molecule. Let us study about rotational degree of freedom. For a body or a system, there may be independent rotations that specify its orientation. There may be rotation of one part of a body with respect to other part. Even in some molecules, this kind of rotation is happen. What is rotational degree of freedom? It represents the number of unique ways the molecule can rotate about its center of mass with a change in molecule's orientation. Rotational degree of freedom happens only in diatomic gas molecules. These molecules have rotational degrees of freedom in addition to the translational degrees of freedom. It is possible in diatomic gas molecules because they are two atoms which are connected together by means of a bond. So there is rotation of one atom with respect to other atom. The given figure shows the two independent axes of rotation 1 and 2 normal to the axis joining the two oxygen atoms about which it can rotate. Two oxygen atoms joined together by a bond. They are two perpendicular axes. There are two rotations possible along these two axes. So, the oxygen molecule will have two rotational degrees of freedom along with 3 translational degrees of freedom. Therefore, rotational degree of freedom contributes a term to the energy that contains a square of a rotational variable of motion. Rotational variable of motion is nothing, it is the angular momentum omega. You know, linear momentum is the product of mass and velocity. So, the angular momentum will be the momentum of a body when it is in rotation. It is numerically equal to mvr, where m be the mass, v be the linear velocity, and r be the radius of circular path through where it has moved about the axis of rotation. It is known to you the linear velocities of a body along three axes are Vx, Vy and Vz, and their corresponding angular velocities are omega x, omega y and omega z. Then how can express the rotational degree of freedom? It is equal to 1 by 2 I1 omega 1 square plus 1 by 2 I2 omega 2 square. In this case, two angular velocities omega 1 and omega 2 are possible about the axes 1 and 2, and I1 and I2 are the corresponding moments of inertia. What is moment of inertia? It is the rotational inertia, where rotational inertia is angular momentum divided by angular velocity. So, in case of oxygen molecule, there will be two rotational degrees of freedom along the two perpendicular axes. The total energy contribution are due to these degrees of freedom for the oxygen molecule. Then there will be three translational degrees of freedom, which are 1 by 2 mx v square, 1 by 2 my vy square and 1 by 2 mz vz square, and two rotational degrees of freedom, which are 1 by 2 I1 omega 1 square and 1 by 2 I2 omega 2 square. On next, I am going to discuss on vibrational degree of freedom. Earlier, we have assumed oxygen molecule is a rigid rotator because it does not vibrate. This assumption is found to be true at moderate temperature. You know, oxygen is diatomic molecule. But the assumption that all diatomic molecules are rigid rotators even at moderate temperature are not valid. At moderate temperature, the atoms in carbon monoxide molecule oscillate along the interatomic axis like a one-dimensional oscillator. Consider two atoms which are carbon and oxygen in carbon monoxide molecule. They vibrate along the interatomic axis. The vibrational energy terms contain squared terms of vibrational variables of motion, which are y and dy by dt. Then total vibrational energy term EV is equal to 1 by 2 m dy by dt whole square plus 1 by 2 k y square, where 1 by 2 m dy by dt whole square be the kinetic energy and 1 by 2 k y square be the potential energy. Here k be the force constant of one-dimensional oscillator and y be the vibrational coordinate. So, there are two terms in the expression for the vibrational energy. From the given figures, first one shows the rotational motion along two axes perpendicular to line joining two atoms, here y and z directions, and second figure shows vibrational motion along line joining the two atoms of a molecule. This slide helps you to compare the translational, rotational and vibrational energy modes of a molecule one with another. The next topic that you are going to study is law of equipartition of energy. From previous class session, you had studied about kinetic interpretation of temperature of gas, according to which the kinetic energy or average kinetic energy of a gas molecule is equal to E by N, which is 3 by 2 kBT. You know, the total internal energy of the gas system, it is E, is utilized by the gas to convert into translational mode of kinetic energy. When they are in translational motion, they should have the kinetic energy. Then the internal energy E is the kinetic energy. So, average kinetic energy of single molecule is equal to total energy E divided by the number of molecules N. It is E by N. Then it is equal to 3 by 2 kBT, where kB be the Boltzmann constant and T be the absolute Kelvin scale of temperature. Then, kinetic energy of a single molecule can be written as 1 by 2 m v square plus 1 by 2 m vy square plus 1 by 2 m vz square, which is the sum of three modes of translational kinetic energy. You know that as the gas system is isotropic, then the square of velocities of the gas molecule along the x-axis, y-axis and z-axis would be same. That is, v square is equal to vy square is equal to vz square. For a gas which is in thermal equilibrium at a temperature capital letter T, the average value of the energy is denoted by E average, which is the sum of average value of kinetic energies along x-axis, y-axis and z-axis. It is equal to average value of 1 by 2 m v square plus average value of 1 by 2 m vy square plus average value of 1 by 2 m vz square, which is equal to 3 by 2 kBT. Since there is no preferred direction, it gives average value of 1 by 2 m v square is equal to average value of 1 by 2 m vy square is equal to average value of 1 by 2 m vz square, which is equal to 1 by 2 kBT. You know, 1 by 2 kBT plus 1 by 2 kBT plus 1 by 2 kBT will be equal to 3 by 2 kBT, which is the average value of kinetic energy of a single molecule. Then, what is law of equipartition of energy? According to this law, in any dynamical system which is in thermal equilibrium, the total energy is equally distributed in all possible energy modes, with each mode will have an average energy equal to 1 by 2 kBT. That is, the energy is equally distributed among its various degree of freedom, and energy associated with each degree of freedom per molecule will be equal to 1 by 2 kBT. Then each translational degree of freedom contributes 1 by 2 kBT. Similarly, each rotational degree of freedom also contributes 1 by 2 kBt, but each vibrational degree of freedom contributes 2 into 1 by 2 kBt, which is equal to kBt. Why? Because a vibrational mode has both kinetic and potential energy mode. The next topic I am going to discuss is specific heat capacity for monoatomic gases, diatomic gases and polyatomic gases. First, let's learn about specific heat capacity for monoatomic gases. You know, monoatomic gases will only have translational degree of freedom. So, they can have 3 translational degrees of freedom. Each degree of freedom will contribute 1 by 2 kBt. Then 3 degrees of freedom will contribute 3 by 2 kBt. By using the law of equipartition of energy, the total internal energy of 1 mole of gas, which is U, is equal to 3 by 2 into kBt into Na. You can understand the total internal energy of n number of gas molecule, which is U, is same as sum of kinetic energy of n number of gas molecules, which is E. Then U should be equal to 3 by 2 kBt into N, as kinetic energy of a single molecule E by N is equal to 3 by 2 kBt. Then what should be the internal energy of 1 mole of gas molecule? It is equal to 3 by 2 kBt into Na. You know that 1 mole of gas molecule will be equal to Avogadro number of gas molecule, which is represented by Na. Then the expression will become as U is equal to 3 by 2 kBt into Na is equal to 3 by 2 into RT. Since the ideal gas equation PV is equal to RT is equal to kBt Na or Na kBt for 1 mole of gas molecule. Here nu is equal to 1. You know that molar specific heat or molar specific heat capacity is the amount of heat energy required by the gas molecule per unit mole to rise the temperature through 1 degree Celsius or 1 Kelvin. Then what should be the molar specific heat capacity at constant volume Cv? It is calculated by taking the derivative of U with respect to T or differentiating the internal energy U with respect to the absolute temperature T. Since U is equal to 3 by 2 RT, then du by dt is equal to 3 by 2 into R into dt by dt. You know 3 by 2 R is the constant. Dt by dt is equal to 1. So du by dt, which is Cv, is equal to 3 by 2 R. For an ideal gas, there is relation between molar specific heat at constant volume and molar specific heat at constant pressure, which is Cp minus Cv is equal to R. You know R be the universal gas constant. By using the expression, which is du by dt is equal to 3 by 2 R, then Cp will be equal to R plus Cv, which is equal to R plus 3 by 2 R. Then Cp will be equal to 5 by 2 R. What should be the ratio of molar specific heat at constant pressure and molar specific heat at constant volume, which is gamma is equal to Cp by Cv is equal to 5 by 2 R by 3 by 2 R. Here 2 and R cancelled, we get gamma is equal to 5 by 3, where gamma be the constant, it is the ratio of Cp to Cv. Now let us calculate specific heat of diatomic gases. In case 1, rigid nature. A rigid diatomic gas means they will have translational as well as rotational degrees of freedom, but they do not have vibrational degree of freedom. They are rigid rotator. A rigid diatomic molecule will have 3 translational degrees of freedom and 2 rotational degree of freedom. Then total number of degrees of freedom will be 5. According to law of equipartition of energy, each degree of freedom will contribute 1 by 2 kBT. Therefore, 5 degrees of freedom will contribute 5 into 1 by 2 kBT is equal to 5 by 2 kBT. Then what should be the total internal energy of 1 mole of gas, which is U is equal to 5 by 2 into kBT into Na. It is equal to 5 by 2 RT. Now we are going to calculate molar specific heat capacity at constant volume, which is Cv is equal to du by dt is equal to 5 by 2 R into dt by dt is equal to 5 by 2 R. Then what should be the molar specific heat capacity at constant pressure? We know that Cp minus Cv is equal to R for an ideal gas. Then specific heat capacity at constant pressure Cp is equal to R plus Cv. Since Cv is equal to 5 by 2 R, then Cp is equal to R plus 5 by 2 R, which is equal to 7 by 2 R. Now we are going to calculate ratio of specific heats, which is the ratio of molar specific heat capacity at constant pressure to molar specific heat capacity at constant volume. It is gamma. Gamma is equal to Cp by Cv is equal to 7 by 2 R by 5 by 2 R. 2 and R are cancelled. We get gamma is equal to 7 by 5. How can calculate specific heat of diatomic gases which are non-rigid? It is the case 2. A non-rigid diatomic gas has translational, rotational as well as vibrational degrees of freedom. So there will be having 3 translational degrees of freedom, 2 rotational degrees of freedom and 1 vibrational degree of freedom. So the total contribution by translational mode will be equal to 3 into 1 by 2 kBT. Rotational degrees of freedom is equal to 2 into 1 by 2 kBT and vibrational degree of freedom is equal to kBT. Then what should be the total internal energy for 1 mole of gas molecule, which is equal to 3 into 1 by 2 kb NAT plus 2 into 1 by 2 kb NAT plus kb NAT. which is equal to 7 by 2 kb NAT is equal to 7 by 2 RT. Now calculate molar specific heat capacity at constant volume. Cv is equal to du by dt is equal to 7 by 2 R. So Cp is equal to Cv plus R, since Cp minus Cv is equal to R. Here Cp is equal to 9 by 2 R. The ratio of molar specific heat capacity at constant pressure to molar specific heat capacity at constant volume, Cp by Cv, which is gamma, is equal to 9 by 7. The given figure shows there are two independent axes of rotation, 1 and 2, which are normal to the axis joining the two oxygen atoms in the oxygen molecule. You know, oxygen is diatomic gas molecule since its molecule contains two atoms. It has 3 translational and 2 rotational degrees of freedom. So, it is a rigid rotator. It does not have vibrational mode of energy. But in case of molecules like carbon monoxide, even at moderate temperatures will show a mode of vibration. Now let us see how to calculate specific heat capacity for polyatomic gases. For polyatomic gases, there will be having 3 translational degrees of freedom, 3 rotational degrees of freedom, and F number of vibrational modes. Then total internal energy of 1 mole of the gas molecules is equal to 3 into 1 by 2 kb NAT plus 3 into 1 by 2 kb NAT plus F into kb NAT. Here kb NAT is the common, so it can be written as 3 by 2 plus 3 by 2 plus F into kb NAT. Since kb NAT is equal to RT, by the ideal gas equation, PV is equal to RT is equal to kb NAT, where nu is equal to 1, which is the number of moles is 1. Then the total internal energy of 1 mole of the gas, U is equal to 3 plus F into RT. Now we are going to calculate Cv and Cp. Cv is equal to du by dt is equal to 3 plus F into R. Since Cp minus Cv is equal to R, so Cp is equal to Cv plus R, where Cv is equal to 3 plus F into R, so Cp is equal to 3 plus F into R plus R, which is equal to 4 plus F into R. What should be the ratio of Cp to Cv? It is gamma is equal to 4 plus F by 3 plus F. Next topic is specific heat capacity for solids. Consider there are n atoms in a solid. Each atom can oscillate about its mean position. The solids do not have translational as well as vibrational modes of energy. Their atoms just oscillate or vibrate about their mean position. Therefore, vibrational degree of freedom of one atom contributes kBT. In one-dimensional motion, average energy will be equal to kBT, and in three-dimensional, its average energy will be equal to 3 into kBT. So, total internal energy U of 1 mole of solid is equal to 3 into kBT into Na, which is equal to 3 RT. Then what should be the specific heat capacity at constant volume? It is du by dt, which is equal to 3R. Now we are going to calculate specific heat capacity at constant pressure according to thermodynamic equation, which is the first law, delta Q is equal to delta U plus P delta V. At constant pressure, change in volume will be very small. It can be neglected, then delta V is equal to 0. So, delta Q is equal to delta U or dQ is equal to du. Then, at constant pressure, specific heat capacity Cp is equal to dQ by dt. As dQ is equal to du, Cp will be equal to du by dt, which is 3R. So, Cp is equal to Cv is equal to 3R. Now we are going to calculate specific heat capacity of water. Consider water as solid, so it will have n number of atoms. Therefore, for each atom, average energy is equal to 3 kBT. Then, total number of atoms in one molecule of water, H2O, is equal to 3. So, what should be the total internal energy of 1 mole of water molecules? It is equal to 3 kBT into 3 into Na, which is 9 RT. Now, Cp is equal to Cv is equal to 9R. The last topic that I am going to discuss is mean free path. It is the average distance between two successive collisions of molecules. You know, inside the gas there are several number of molecules which are moving in straight line and take part in random collision. So, mean free path is defined as the distance which a particular gas molecule travels without colliding. How can express the mean free path mathematically? Consider each gas molecule is a sphere of diameter d. The average speed of each molecule is v. Suppose the molecule suffers collision with any other molecule within the distance d. And suppose that any molecule which comes within the distance range of diameter of another molecule will have collision with that molecule. As shown in given figure, we have considered d as the diameter of the gas molecule, and it should be equal to the radius of the imagined cylindrical region through where the gas molecule shifts in time delta t. So, in time delta t, it will shift a volume of pi d square v delta t, wherein any other molecule will collide with it. So, the volume within which a molecule suffer collision is equal to pi d square v delta t, which is equivalent to pi d square h, where h be the v delta t is equal to average velocity multiplied by the time delta t. It is the distance traveled by the molecule in time delta t. Let number of molecules per unit volume be small letter n. Therefore, the total number of collisions in time delta t is equal to pi d square v delta t into n. Then, what should be the rate of collision? It is total number of collision divided by time, which is equal to v pi d square delta t into n by delta t is equal to v pi d square n. Suppose time between two successive collisions be capital letter T. How can find this value? It is calculated by dividing the total time taken for number of collisions divided by total number of collisions, or it is just reciprocal of rate of collision. It is equal to 1 by v pi d square n. Then average distance between two successive collisions, or the mean free path, which is L is equal to t into average speed, which is equal to 1 by pi d square n. You know that distance is equal to speed into time. In this derivation, we imagined the other molecules to be at rest. But actually, all molecules are moving and the collision rate is determined by the average relative velocity of the molecule. Thus, this value 1 by pi d square n should be modified and a factor root 2 is introduced. Then mean free path L is equal to 1 by root 2 pi d square n. What are the factors upon which mean free path depend? One is number density, or number of molecules per unit volume, and second one is size of the molecule. Mean free path depends inversely on number density and size of the molecule. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.